Right now, 25 billion kilometers from where you are sitting, a machine built in 1977 is picking up a signal from a place no human instrument was ever built to reach. No spacecraft has ever transmitted from this far away and stayed in contact. No sensor sent to study interstellar space has functioned this long, this far from home. No model built before 2012 predicted what this machine is still hearing today. It is not silence out there. It is a signal. Stay with me, because NASA has now confirmed exactly what that signal is, and what it means is still being argued over in the scientific literature right now. If you're new here, this channel breaks down real space missions with real data, no filler. Subscribe if that's your thing. Let us go back to the beginning. Voyager 1 launched on September 5th, 1977 from Cape Canaveral. 16 days after its twin, Voyager 2, lifted off the same pad. The plan was modest, a 4-year tour past Jupiter and Saturn, then quietly conclude. NASA's original ambition had been bigger, a grand tour past all 4 outer giants, but budget cuts trimmed it down to something Congress would actually pay for. So engineers built 2 probes instead of a fleet, gave each one 10 scientific instruments, a 12-foot dish antenna, and 3 nuclear batteries, radioisotope thermoelectric generators that convert the heat of decaying plutonium into electricity. At launch, those batteries produced about 470 watts, roughly enough to run a couple of hairdryers. Nobody on the original team expected them to still be running half a century later, and to be fair to them, there was no reason they should have. Spacecraft electronics from the disco era were not engineered with 50-year lifespans in mind. Every year, Voyager 1 has kept transmitting past. That original 4-year window has been, quite literally, borrowed time. The mission's real prize was never just the 2 planets, it was the edge. Before any of that, though, Voyager 1 did the job it was actually funded to do, and did it well. It swung past Jupiter in March 1979, revealing active volcanoes on the moon Io, the first time volcanic activity had ever been observed anywhere beyond Earth. It reached Saturn in November 1980, returning close-up images of the rings and a detailed look at the giant moon Titan, thick with its own hazy nitrogen atmosphere. That close pass by Titan bent Voyager 1's trajectory sharply upward, out of the flat plane where all the planets orbit, ending its tour of the solar system for good, and sending it climbing toward the stars instead. Everything that followed, the long silence between planets, the years of drifting, the eventual crossing into interstellar space, happened because of a single gravitational nudge from one moon, 46 years ago. Scientists modeled the solar system as a bubble, called the heliosphere, inflated outward by the solar wind, the constant stream of charged particles boiling off the sun. Past a certain distance, that pressure should fade, and interstellar space, the vast near vacuum between stars, should begin. That boundary was named before anyone had measured it, the heliopause. This wasn't a guess. Scientists had tracked the solar wind's behavior for decades, and the physics of an expanding bubble meeting the faint. Resistance of the galaxy's own particle wind is solid, testable science. The model made a specific, falsifiable prediction. Plasma density inside the heliosphere sits around 0.02 of a particle per cubic centimeter, while true interstellar space should show roughly 1/10 of a particle per cubic centimeter. A jump of about 50 times. Remember that number. Everything that follows depends on it. Voyager 1 reached the inner edge of that boundary region, called the termination shock, in December 2004, and kept climbing outward for 8 more years. On August 25th, 2012, at a distance of about 121 astronomical units from the Sun, 121 times farther out than Earth itself sits, the readings changed abruptly. The steady stream of solar particles Voyager had tracked for 3 decades all but vanished. Cosmic rays from deep in the galaxy, normally filtered out by the Sun's magnetic bubble, spiked hard. Every info, direct sign said Voyager 1 had just left home. There was one serious problem. The spacecraft's dedicated plasma density sensor had died back in 1980, shortly after the Saturn flyby. Voyager had apparently crossed the single most significant boundary of its entire mission, and the one instrument built to prove it directly was already broken. Here's where it gets complicated before it gets confirmed. For nearly a year, scientists argued from incomplete evidence. The magnetic field data was especially frustrating. By every model, field direction should have shifted noticeably once Voyager crossed into interstellar space, but it barely changed at all, leaving some researchers genuinely uncertain whether the spacecraft had left the solar system or was sitting in some unmodeled transitional zone. Then, in April 2013, the Sun handed the mission an accident of good timing. A massive solar eruption sent a shockwave rippling outward through the solar system, and roughly 13 months later that shockwave slammed into the plasma surrounding Voyager 1, far out in what should have been interstellar territory. The impact rang the local plasma like a struck bell, and Voyager's surviving plasma wave instrument, not a density sensor, but something that could detect the vibration of disturbed plasma, caught the tone. The oscillation frequency corresponded to an electron density of about 0.08 particles per cubic centimeter. Sit with that for a second, because it lands almost exactly on the number the models predicted for genuine interstellar space, confirmed not by direct measurement, but by an accident of solar weather, arriving at the one instrument on the entire spacecraft still capable of hearing it. And this is not a photograph confirming a hunch. This is a bell rung by a coincidence, heard 300 million kilometers away, 400 days after it happened. Translate that density into something you can picture. A tenth of a particle in a space the size of a sugar cube is still an almost incomprehensible void by any everyday standard. Interstellar space remains colder and thinner than the best vacuum chamber ever built on Earth. But compared to the near total emptiness of the heliosphere Voyager had just left, it represented a wholly different physical regime, the difference between an empty concert hall and one with a scattering of people finally seated inside it. Not crowded, but no longer silent. And that distinction between silent and not silent turned out to matter enormously, because 8 years after that first accidental detection, a discovery buried in the same instrument's data quietly rewrote what receiving a signal from interstellar space actually meant. Here's the finding NASA has since confirmed, and the reason this title isn't exaggeration. The 2013 detection had depended entirely on luck, a solar shockwave happening to strike the right patch of plasma at the right moment 600 days after leaving the Sun, with Voyager positioned to catch it. Scientists assumed after that they'd be stuck waiting years between usable readings, catching a glimpse of interstellar plasma only when the Sun cooperated. But when Cornell astronomer Stella Ocker and her colleagues went back through plasma wave data collected from 2017 onward, they found something that had no business being there by the old model: a faint, narrow, continuous emission, present reading after reading, with no solar shockwave anywhere nearby. Published in Nature Astronomy in May 2021, the paper documented what the team called a persistent plasma wave signal, a genuine, ongoing transmission from the interstellar medium itself, picked up by Voyager 1's instrument not once, not during a lucky collision, but continuously, month after month. NASA's own public statements on the finding were direct. Voyager 1 was, for the first time, providing an essentially uninterrupted signal from beyond the edge of the solar system, rather than the occasional lucky echo scientists had settled for since 2013. Cornell astronomer Shami Chatterjee, a co-author on the study, put it about as plainly as a scientist ever puts anything. Regardless of what the Sun happens to be doing on any given day, Voyager is sending back detail, continuously reporting the density it is moving through right now, and then right now again and again, on a spacecraft that will simply keep doing this for as long as it has power to transmit. Here's where it gets worse for the old assumption and better for the mission. The density measured through that persistent signal wasn't flat either. As Voyager kept moving outward, sampling roughly every hundredth of an astronomical unit, an absurdly fine resolution for a measurement made 10 billion miles from the nearest technician, researchers found real, structured fluctuations in the plasma, small-scale turbulence layered on top of a slow, broader rise in density the farther out the spacecraft traveled. Read that again. The deeper into interstellar space Voyager pushed, the denser the plasma around it. Tended to get, on average, not sparser, riding on top of a choppy, unpredicted texture. What most people are not seeing when this story gets told casually is that this signal is not a metaphor. It is a literal, sustained wave of plasma oscillation, arriving at Voyager's antenna the way a radio signal arrives at a receiver, and scientists can now track it in near real time instead of waiting for the Sun's next tantrum. Here's where this stops being abstract. Every kilometer of that plasma sits between Earth and the unfiltered radiation of the rest of the galaxy, and the same bubble Voyager is now outside of has been shielding human civilization from the full blast of galactic cosmic rays for the entire span of recorded history. Understanding exactly how dense, how turbulent, and how structured the region just beyond that shield really is, isn't an academic footnote. It's a direct input into every serious proposal for sending astronauts beyond the protection of the Sun's magnetic bubble, and into every model of how much of that radiation actually leaks into the inner solar system in the first place. Voyager 1 isn't exploring an abstract line on a diagram. It is mapping the walls of the only shelter our entire species has ever had. But before any of that data could keep flowing home, Voyager itself nearly went silent for good. And the story of how engineers pulled it back is, on its own, one of the more remarkable rescues in the history of spaceflight. In November 2023, Voyager 1 began sending back telemetry that made no sense at all. Not silence, something worse. A repeating, garbled pattern of ones and zeros, as if the spacecraft were speaking, but in no language anyone at JPL could parse. The engineering data that normally reported the health of the spacecraft's systems had effectively turned to static. For a machine 46 years into its mission, transmitting from a distance where a single round-trip command and response cycle takes the better part of 2 days, This was about as close to a nightmare scenario as the Voyager team could imagine. Every engineer on that team understood exactly what a full loss of signal would mean. No repair vehicle exists that could ever reach it. No backup spacecraft was ever built to take its place, and once contact is truly severed, there would be no second attempt. Think about what a spacecraft this old actually is. No modern operating system, no wireless update channel, no diagnostic app to run. Every fix has to be composed as raw commands, tested first against ground-based replicas of 49-year-old hardware, then fired blind across a gap that keeps widening by the day. The team suspected the problem lived somewhere inside the flight data system, the onboard computer responsible for packaging science and engineering data before transmission. Over months of painstaking work, commands sent, responses awaited nearly 2 days later, results analyzed, next commands drafted. Engineers eventually traced the fault to a single corrupted chip inside that computer's memory, storing a small piece of code essential to formatting the spacecraft's data correctly. They could not fly out and replace it. They could not even be entirely certain what specific memory address had failed, because the very system meant to report that failure was the one malfunctioning. So they did something almost absurdly elegant. They rewrote the affected code and split it into pieces small enough to be redistributed across other areas of the computer's memory that were still functioning, reprogramming a 50-year-old spacecraft's brain, one careful transmission at a time, from a room on Earth 24 billion kilometers away. In April 2024, after roughly 5 months of near-total silence, Voyager 1 sent back coherent engineering data again. Then, months later, in October 2024, a fresh crisis hit. After engineers activated a heater on the spacecraft, an automatic fault protection system tripped, shutting off Voyager 1's primary radio transmitter entirely, and forcing the team onto a backup transmitter that had not been used since 1981, carrying a signal barely audible against the deep space background. It took engineers until mid-November to fully restore the primary channel. Each crisis, the same quiet, unglamorous heroism. Humans, patient enough to wait 2 full days for every single reply, coaxing 1 more year of conversation out of a machine that, by any reasonable engineering standard, should have gone silent decades ago. Here's what is happening right now in 2026. Voyager 1's 3 nuclear batteries are losing roughly 4 watts of power every single year. A slow, steady bleed with no way to reverse it, since the plutonium inside them decays on its own physical clock, regardless of what anyone on Earth does. What began as 470 watts at launch has fallen to roughly a quarter of that. Of the 10 scientific instruments Voyager 1 carried into space, only a handful still function at all. And the mission team has had to make an increasingly brutal set of choices about which ones stay alive. On February 27, 2026, during a routine maneuver, the spacecraft's power levels dropped unexpectedly, coming dangerously close to triggering an automatic protective shutdown that would have forced engineers into another lengthy, risky recovery. Rather than wait for that failure to happen on its own terms, the team acted first. On April 17, 2026, they sent the command to permanently power down the low-energy charged particles instrument, the very detector that had helped confirm the 2012 heliopause crossing in the first place, leaving Voyager 1 with exactly 2 working science instruments, the plasma wave system still catching that persistent interstellar signal, and a magnetometer tracking the shape of the local magnetic field. 2 instruments out of 10, 49 years in, still working according to the mission's own project managers, and still sending that signal home from a region of space no other human-made object has ever reached. Power is not the only thing failing either. Some of the small hydrazine thrusters that keep Voyager 1's high-gain antenna pointed precisely at Earth have clogged over the decades, and the spacecraft, no longer has a working backup for that system. Every remaining component on board is now what engineers call single-string, meaning there is exactly one of it, with no second copy waiting if it fails. Suzanne Dodd, the mission's project manager, has described the spacecraft in blunt terms. Everything about it now runs without a safety net. The team's next move is something they've nicknamed only half-jokingly the Big Bang, a single coordinated swap of multiple power-hungry components for lower power alternatives, executed all at once rather than gradually, to buy each spacecraft years instead of months. It was tested first on Voyager 2, the slightly less power-starved twin, in May and June of 2026. Or, if that test succeeds, the same maneuver is planned for Voyager 1 no earlier than this July, which means, as this video reaches you, engineers at JPL may be in the process of performing open-heart surgery on a computer 25 billion kilometers away, with a 2-day delay between every incision and every confirmation that the patient survived it. And in a few months, something happens with no ambiguity at all, no room for debate, a date locked in by nothing more complicated than distance and the constant speed of light. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific Standard Time, Voyager 1 will be exactly 96 miles from Earth. A light day away, the distance a beam of light travels in 24 uninterrupted hours. Suzanne Dodd, the Voyager project manager at JPL, has described what that will actually feel like for the people running the mission. If she sends a command and says, "Good morning, Voyager," at 8 in the morning on a Monday, she will not hear its answer until 8 in the morning on Wednesday. Not because anything is wrong, because that is simply how long it now takes for a signal to cross the gap between a machine humanity built in 1977 and the hands still tending it today. From that date forward, every single exchange with Voyager 1 will carry a minimum 2-day round trip permanently, for as long as the mission continues. Now, the honest part, the part that doesn't resolve neatly, because it hasn't resolved yet in the actual scientific literature. What exactly generates the persistent plasma signal Voyager has been receiving since 2017 is still not fully settled. The Nature Astronomy paper that first identified it lays out competing explanations, rather than a single confirmed cause. The emission could be the result of thermally excited plasma oscillations, tiny random vibrations that occur naturally in any warm plasma, even with nothing dramatic driving them, or it could be a form of quasi-thermal noise, a broader statistical hiss produced by the collective jostling of charged particles in the local interstellar medium. Both are physically plausible. Neither has been definitively confirmed as the sole cause, and the researchers themselves were explicit that a fuller answer would require either new Voyager data or an entirely new interstellar mission to clarify. It is worth being precise about what this uncertainty does and does not mean. It does not mean the signal itself is in doubt. The emission is real. It has been independently verified across years of continuous readings, and NASA's own confirmation of the finding is not in question. What remains open is narrower and, in some ways, more interesting. Not whether Voyager is receiving something, but exactly what physical process out in that near-empty plasma is generating it in the first place. What most people are not seeing when this story gets told is that we don't fully know the mechanism is not scientific failure. It's the honest, current state of a measurement being made in a region of space where no other instrument has ever operated long enough to check the work. Step back from the plasma readings and the power budgets for a moment, and there's a larger pattern worth sitting with. Voyager 1 was never designed to still be transmitting in 2026. It was built to survive a 4-year tour of 2 planets. Using engineering standards from an era before the personal computer, memory measured in kilobytes rather than gigabytes, radio transmitter engineers now have to wait carefully, aware that any wrong move could end the conversation permanently. And yet, it is that same aging, deteriorating, power-starved machine that keeps handing scientists genuinely new physics. A heliopause crossing, confirmed by cosmic accident, a persistent interstellar signal nobody predicted, a density gradient that still doesn't perfectly match the models built to describe it. This is the pattern underneath almost every real leap in how humanity understands its place in the universe. Not a single triumphant discovery arriving on schedule, but old instruments pushed past their intended lifespans, returning data nobody built them expecting to receive, forcing the models to catch up to the machine rather than the other way around. Think about what that means for how we plan the next 50 years of exploration. Every mission NASA launches today is designed, budgeted, and reviewed against a specific expected lifespan, and Voyager 1 is the permanent, uncomfortable reminder that the most valuable data a spacecraft ever returns might arrive decades after everyone involved in building it has retired or died, waiting on discoveries nobody wrote into the original proposal. The scientists reading Voyager's persistent signal in 2021 were not the scientists who designed the plasma wave instrument in the 1970s. Some of them were not yet born when it launched. That's not a footnote. That's the actual mechanism by which this kind of science works. One generation builds the ear, and a later generation finally learns how to listen with it. It also means the confirmation in this story's title is not really an ending. It is a status update on an instrument that is still running, still transmitting, still capable of handing the next generation of researchers something nobody currently working on the mission has thought to look for yet. There's a small, easily overlooked detail buried in the mission records that lingers longer than any of the numbers. Voyager 1's cameras were switched off permanently in 1990, their software stripped from the spacecraft's memory to free up power for instruments considered more essential to the journey ahead. The machine gave up sight so it could keep listening, and what it has heard in the decades since is a universe that does not go quiet just because there is no one there to see it. A signal humming faintly in the dark, arriving now continuously instead of by accident, one day later than whenever it was actually made, received by a handful of engineers on Earth who still, every single time, wait for the reply before they let themselves believe it worked. Somewhere on that same spacecraft, bolted to its side, a gold-plated record still carries greetings in 55 languages and a map showing the way home, traveling outward now, regardless of whether anyone is left to hear it, indefinitely, long after the last watt of power finally runs out. So here's everything in one breath. Voyager 1 launched in 1977 on a 4-year mission and crossed into interstellar space in 2012. A crossing scientists could only confirm a year later thanks to a lucky solar shockwave ringing the plasma like a bell. In 2021, researchers confirmed something the old models never predicted: a persistent, continuous plasma signal from interstellar space that Voyager has been receiving since 2017, letting scientists track the density of the region beyond our sun in near real time instead of waiting for accidents. A catastrophic computer glitch nearly ended the mission in 2023 and 2024, fixed by engineers reprogramming the spacecraft's memory one careful 2-day delayed command at a time. Today, in 2026, only 2 of Voyager's original 10 instruments still function. Power keeps bleeding away at 4 watts a year, and in November the spacecraft will cross the 1 light day mark, a threshold that will make every future exchange with it take a minimum of 48 hours round trip. And the exact physical cause of that persistent interstellar signal it first started catching in 2017 is, right now, still not fully resolved. If any part of this made you want to see where the story goes next, because there is a next chapter, whether the Big Bang power swap saves Voyager 1 this July, or the mission finally goes quiet trying, hit subscribe and turn on notifications, because I'll be covering that outcome the moment it's confirmed. One question before you go: if you had to choose, would you rather NASA spend its resources trying to keep this 50-year-old machine alive a few more years, or accept its silence and put everything into building something new to take its place? Let me know in the comments. I rate every single one.